Chapter 10. Physical Security Requirements. The CISSP exam topics covered in this chapter include Domain 3.0, Security Architecture and Engineering. 3.8, Apply security principles to site and facility design. 3.9, Design site and facility security controls. 3.9.1, Wiring closets/intermediate distribution facilities. 3.9.2, Server rooms/data centers. 3.9.3, Media storage facilities. 3.9.4, Evidence storage. 3.9.5, Restricted and work area security. 3.9.6, Utilities and heating, ventilation and air conditioning, HVAC. 3.9.7, Environmental issues. 3.9.8, Fire prevention, detection and suppression. 3.9.9, Power, for example, redundant backup. Domain 7, Security Operations. 7.14, Implement and manage physical security. 7.14.1, Perimeter security controls. 7.14.2, Internal security controls. The topic of physical and environmental security is referenced in several domains. The two primary occurrences are in Domain 3.0, Security Architecture and Engineering, and Domain 7.0, Security Operations. Several subsections of these two domains of the CISSP certification exam deal with topics and issues related to facility security, including foundational principles, design and implementation, fire protection, perimeter security, internal security, and many more. This chapter explores these issues and discusses safeguards and countermeasures to protect against them. In many cases, you'll need a disaster recovery plan or a business continuity plan should a serious physical threat, such as an explosion, sabotage, or natural disaster occur. Chapter 3, Business Continuity Planning, and Chapter 18, Disaster Recovery Planning, cover those topics in detail. Apply security principles to site and facility design. Without control over the physical environment, no collection of administrative, technical, or logical security controls can provide adequate protection. If a malicious person can gain physical access to your facility or equipment, they can do just about anything they want, including destruction, disclosure, and alteration. There are many aspects of implementing and maintaining physical security. A core element is selecting or designing the facility to house your IT infrastructure and your organization's operations. The process of selecting or designing facility security always starts with a plan. Secure Facility Plan. A secure facility plan outlines the security needs of your organization and emphasizes methods or mechanisms to employ to provide security. Such a plan is developed through risk assessment and critical path analysis. Critical path analysis is a systematic effort to identify relationships between mission-critical applications, processes, and operations, and all the necessary supporting elements. For example, an online store relies on internet access, computer hardware, electricity, temperature control, storage facilities, and so on. When critical path analysis is performed properly, a complete picture of the interdependencies and interactions necessary to sustain the organization is produced. The first step in designing a secure IT infrastructure is providing security for the basic requirements of the organization and its computers. These basic requirements include electricity, environmental controls, in other words, a building, air conditioning, heating, humidity control, and so on, and water/sewage. While examining for critical paths, it is also important to evaluate completed or potential technology convergence. Technology convergence is the tendency for various technologies, solutions, utilities, and systems to evolve and merge over time. Often, this results in multiple systems performing similar or redundant tasks, or one system taking over the features and abilities of another. Though in some instances, this can result in improved efficiency and cost savings, it can also represent a single point of failure and become a more valuable target for malicious hackers and intruders. For example, if voice, video, building control, storage, that is NAS, and productivity traffic all share a single connection path rather than individual paths, a single act of sabotage to the main connection is all that is required for intruders or thieves to sever external communications. Security staff should participate in site and facility design considerations. Otherwise, many important aspects of physical security essential for the existence of logical security may be overlooked. With security staff involved in the physical facility design, you can be assured that your long-term security goals as an organization will be supported not just by your policies, personnel, and electronic equipment, but also by the building itself. A secure facility plan is based on a layered defense model. Only with overlapping layers of physical security can a reasonable defense be established against would-be intruders. Physical security should be thought of as establishing an obstacle course or gauntlet that attackers have to attempt to work their way through. Thus, security mechanisms are positioned to operate in series rather than in parallel to optimize the difficulty in breaching the protective infrastructure. Site selection. Site selection should be based on the security needs of the organization. Cost, location, and size are important, but addressing the requirements of security should always take precedence. Securing assets depends largely on site security, which involves numerous considerations and situational elements. Site location and construction play a crucial role in the overall site selection process. Proximity to other buildings and businesses is a crucial consideration. What sorts of attention do they draw, and how does that affect your operation or facility? If a nearby business attracts too many visitors, generates lots of noise, causes vibrations, or handles dangerous materials, they could harm your employees or buildings. Proximity to emergency response personnel is another consideration, along with other elements. At a minimum, ensure that the building is designed to withstand typical extreme weather conditions for the area, and that it can deter or fend off most overt break-in attempts. Vulnerable entry points such as windows and doors tend to dominate such analysis, but you should also evaluate objects, trees, shrubs, planters, columns, storage buildings, or other person-made items that can obscure break-in attempts. Does your organization need to be easily accessed and thus clearly visible? Or would it be a better design to not stand out? Industrial camouflage is the attempt to mask or hide the actual function, purpose, or operations of a facility by providing a facade presenting a believable or convincing alternative. For example, a data center may present itself as a food packing facility. Facility design. The top priority of security should always be the protection of the life and safety of personnel. To that end, be sure that all facility designs and physical security controls are in compliance with all applicable laws and regulations. These may include health and safety requirements, building codes, labor restrictions, and more. In the United States, some common regulations to follow in regard to facility security are guidelines and requirements from Occupational Safety and Health Administration, OSHA, and the Environmental Protection Agency, EPA. For most organizations, it may be worthwhile to have a facility security officer to assist with the design, implementation, management, and oversight of facility security. Important issues to consider include combustibility, fire rating, construction materials, load rating, placement and control of items such as walls, doors, ceilings, flooring, HVAC, power, water, sewage, gas, and so on. Forced intrusion, emergency access, resistance to entry, direction of entries and exits, use of alarms, and conductivity are other important aspects to evaluate. Every element within a facility should be evaluated in terms of how it could be used for and against the protection of the IT infrastructure and personnel. For example, positive flows for air and water from inside a facility to outside its boundaries. There's also a well-established school of thought on secure architecture that's often called crime prevention through environmental design, CPTED. CPTED addresses facility design, landscaping, entrance concepts, campus layouts, lighting, road placement, and traffic management of vehicles and those on foot. The core principle of CPTED is that the design of the physical environment can be managed, manipulated, and crafted with intention in order to create behavioral effects or changes in people present in those areas that result in reduction of crime, as well as a reduction of the fear of crime. Just think of a dark back alley with sunken doorways and several large trash dumpsters. Then compare that to a well-lit street with a broad sidewalk with attractive storefronts. Notice the feelings you have about those locations just by thinking about them. CPTED design-guided locations have an amazing but subtle effect on the behaviors of people as well as their perceptions of a location. CPTED has numerous recommendations and suggestions for improving facility design for security purposes, such as the following. Keep planters under 2.5 feet tall. This prevents them from being used to hide behind or as a step to reach a window. Keep decorative elements small or far away from the building. Locate the data center at the core of the building. Provide benches and tables to encourage people to sit and look around. They provide a type of automatic surveillance. Mount cameras in full view to act as a deterrent. Keep entrances open and clear, that is, without obstacles like trees or columns, so that visibility can be maintained. Keep the number of entrances to a minimum, and close off doorways during evenings or weekends when fewer workers are present. Provide parking for visitors near the entrance. Make delivery access driveways and entrances less visible or noticeable to the public. For example, by positioning them on the back of the building and requiring the use of an alternate road. CPTED has three main strategies: natural access control, natural surveillance, and natural territorial reinforcement. Natural access control is the subtle guidance of those entering and leaving a building through placement of entranceways, use of fences and bollards, and placement of lights. The idea here is to make the entrance point to a building look like an entrance point without having to resort to giant signs saying, "Enter here." This can also extend internally by creating security zones to distinguish the general access areas from those of higher security that require certain classification or job responsibilities to enter. Those areas of the same access level should be open, inviting, and easy to move around in. But those areas that are restricted or closed off should seem more difficult to access and require more effort and intention of the individual to access. Natural surveillance is any means to make criminals feel uneasy through the increasing of opportunities for them to be observed. This can be accomplished by an open and obstacle-free outside area, especially around entrances, with clear lines of sight. This can be further increased by encouraging workers and even the public to loiter around the area by providing a pleasing landscape, not directly against the buildings, with plenty of seating. Walkways and stairways should be open so that others nearby can easily see if someone is present. And all areas should be very well lit throughout the day, but especially at night. Natural territorial reinforcement is the attempt to make the area feel like an inclusive, caring community. The area should be designed so that it looks cared for and respected, and that it is actively being defended. This can be accomplished with decorations, flags, lighting, landscaping, presentations of company logos, clearly visible building numbers, and decorative sidewalks and other architectural features. This approach may cause intruders to feel like they don't belong, and that their activities would be at a higher risk of being detected. The International Septet Association is an excellent source for information on this subject. cpted.net, as is Oscar Newman's book, Creating Defensible Space, published by HUD's Office of Policy Development and Research. You can obtain a free PDF download at huduser.gov/publications/PDF/def.pdf. The use of Septet does not substitute for the use of actual target hardening, such as locked doors, security guards, fences, and bollards. However, a mixture of traditional physical barriers and Septet strategies can provide both preventive security and detective and deterrent security. Implement site and facility security controls. The grouping of controls named physical should be called facility instead, since the controls for protecting a facility include policies, personnel management, computer technology, and physical barriers. So just calling this grouping physical is not as accurate as it could be, but physical is the accepted terminology. Administrative physical security controls include facility construction and selection, site management, building design, personnel controls, awareness training, and emergency response and procedures. Technical physical security controls include building access controls, intrusion detection, alarms, security cameras, monitoring, heating, ventilation and air conditioning, HVAC power supplies, and fire detection and suppression. Physical controls for physical security include fencing, lighting, locks, construction materials, access control vestibules, formerly known as man-traps, guard dogs, and security guards. When designing physical security for an environment, focus on the functional order in which controls should be used. A common order of operations is as follows: 1. Deter, 2. Deny, 3. Detect, 4. Delay, 5. Determine, 6. Decide. Security controls should be deployed so that initial attempts to access physical assets are deterred. Boundary restrictions accomplish this. If deterrence fails, then direct access to physical assets should be denied. For example, locked vault doors. If denial fails, your system needs to detect intrusion. For example, using motion sensors. If the breach is successful, then the intruder should be delayed sufficiently in their access attempts to enable authorities to respond. For example, a cable lock on the asset. Security staff or legal authorities should determine the cause of the incident or assess the situation to understand what is occurring. Then, based on that assessment, they should decide on the response to implement, such as apprehending the intruder or collecting evidence for further investigation. Tip: a cable lock is used to protect smaller devices and equipment by making them more difficult to steal. A cable lock usually isn't an impenetrable security device. since most portable systems are constructed with thin metal and plastic. However, a thief will be reluctant to swipe a cable-locked device because the damage caused by forcing the cable lock out of the security/lock slot will be obvious when they attempt to pawn or sell the device. Equipment failure. Preparing for equipment failure can take many forms. In some non-mission critical situations, simply knowing where you can purchase replacement parts for a 48-hour replacement timeline is sufficient. In other situations, maintaining on-site replacement parts is mandatory. Keep in mind that the response time in returning a system to a fully functioning state is directly proportional to the cost involved in maintaining such a solution. Costs include storage, transportation, pre-purchasing, and maintaining on-site installation and restoration expertise. In some cases, maintaining on-site replacements is not feasible. For those cases, establishing a service level agreement, SLA, with the hardware vendor is essential. An SLA clearly defines the response time a vendor will provide in the event of an equipment failure emergency. Equipment failure is a common cause of a loss of availability. When deciding on strategies to maintain availability, it is often important to understand the criticality of each asset and business process, as well as the associated allowable interruption window, AIW, service delivery objective, SDO, and maximum tolerable downtime/outage, MTD/MTO. These ranges, boundaries, and objectives help focus on the necessary strategies to maintain availability, or at least minimize downtime while optimizing cost efficiency. Aging hardware should be scheduled for replacement and/or repair. The schedule for such operations should be based on the mean time to failure, MTTF, and mean time to repair, MTTR estimates established for each device, or on prevailing best organizational practices for managing the hardware lifecycle. MTTF is the expected typical functional lifetime of the device given a specific operating environment. Be sure to schedule all devices to be replaced before their MTTF expires. MTTR is the average length of time required to perform a repair on the device. A device can often undergo numerous repairs before a catastrophic failure is expected. An additional measurement is that of the mean time between failures, MTBF. This is an estimation of the time between the first and any subsequent failures. If the MTTF and MTBF values are the same or fairly similar, manufacturers often only list the MTTF to represent both values. When a device is sent out for repairs, you need to have an alternate solution or a backup device to fill in for the duration of the repair time. Often, waiting until a minor failure occurs before a repair is performed is satisfactory. But waiting until a complete failure occurs before replacement is an unacceptable security practice. Wiring closets. A cable plant management policy is used to define the physical structure and deployment of network cabling and related devices within a facility. A cable plant is the collection of interconnected cables and intermediary devices, such as cross-connects, patch panels, and switches, that establish the physical network. Elements of a cable plant include the following: entrance facility, also known as the demarcation point or MDF. This is the entrance point to the building where the cable from the provider connects the internal cable plant. Equipment room. This is the main wiring closet for the building, often connected to or adjacent to the entrance facility. Backbone distribution system. This provides wired connections between the equipment room and the telecommunications room, including cross-floor connections. Wiring closet. This serves the connection needs of a floor, or a section of a large building by providing space for networking equipment and cabling systems. It also serves as the interconnection point between the backbone distribution system and the horizontal distribution system. The wiring closet is also known as premises wire distribution room, main distribution frame, MDF, intermediate distribution frame, IDF, and telecommunications room, and it is referred to as intermediate distribution facilities in ISC squared CISSP Objective 3.9.1. Horizontal distribution system. This provides the connection between the telecommunications room and work areas, often including cabling, cross-connection blocks, patch panels, and supporting hardware infrastructure such as cable trays, cable hangers, and conduits. Protected cable distribution or protective distribution systems, PDSs, are the means by which cables are protected against unauthorized access or harm. The goals of PDSs are to deter violations, detect access attempts, and otherwise prevent compromise of cables. Elements of PDS implementation can include protective conduits, sealed connections, and regular human inspections. Some PDS implementations require intrusion or compromise detection within the conduits. Wiring closets also serve as a convenient location to link multiple floors together. In such a multi-story configuration, the wiring closets are typically located directly above and below each other on their respective floors. Wiring closets are also commonly used to house and manage the wiring for many other important elements of a building, including alarm systems, circuit breaker panels, telephone punch-down blocks, wireless access points, telephone services, and video systems, including security cameras. Wiring closet security is extremely important. Most of the security for a wiring closet focuses on preventing physical unauthorized access. If an unauthorized intruder gains access to the area, they may be able to steal equipment, pull or cut cables, or even plant a listening device. Thus, the security policy for the wiring closet should include a few ground rules, such as the following. Never use the wiring closet as a general storage area. Have adequate locks, which might include biometric elements. Keep the area tidy. Do not store flammable items in the area. Set up video surveillance to monitor activity inside the wiring closet. Use a door open sensor to log entries. Do not give keys to anyone except the authorized administrator. Perform regular physical inspections of the wiring closet's security and contents. Include the wiring closet in the organization's environmental management and monitoring in order to ensure appropriate environmental control and monitoring, as well as to detect damaging conditions such as flooding or fire. It is also important to notify your building management of your wiring closet security policy and access restrictions. Doing so will further reduce unauthorized access attempts. Server rooms/data centers. Server rooms, data centers, communications rooms, server vaults, and IT closets are enclosed, restricted, and protected rooms where your mission-critical servers and network devices are housed. A server room is often configured as a lights-out area, which is generally designed to improve efficiency. A server room is often not optimized for workers, but for housing of equipment. Data centers can include gas-based halon substitute oxygen displacement fire detection and extinguishing systems, walls with a 1-hour minimum fire rating, low temperatures, little or no lighting, and equipment stacked with little room to maneuver. Server rooms should be designed to support optimal operation of the IT infrastructure and to block unauthorized human access or intervention. Server rooms should be located at the core of the building. Try to avoid locating these rooms on the ground floor, on the top floor, and in the basement whenever possible. Additionally, the server rooms should be located away from water, gas, and sewage lines. These pose too large a risk of leakage or flooding, which can cause serious damage and downtime. For many organizations, their data center and their server room are one and the same. For some organizations, a data center is an external location used to house the bulk of their back-end computer servers, data storage equipment, and network management equipment. This could be a separate building near the primary offices, or it could be a remote location. A data center might be owned and managed exclusively by your organization, or it could be a leased service from a data center provider, such as a CSP or co-location center. A data center could be a single-tenant configuration or a multi-tenant configuration. In many data centers and server rooms, a variety of technical controls are employed as access control mechanisms to manage physical access. These include, but are not limited to, smart/dumb cards, proximity devices and readers, biometrics, intrusion detection systems, IDSs, focusing on physical intruders, and a design based around defense in depth. Smart cards and badges. Badges, identification cards, and security IDs are forms of physical identification and/or electronic access control devices. A badge can be as simple as a name tag indicating whether you are a valid employee or a visitor, sometimes called a dumb card. Or it can be as complex as a smart card or token device that employs multi-factor authentication to verify and prove your identity and provide authentication and authorization to access a facility, specific rooms, or secured workstations. Badges may be color-coded by facility or classification level, and they often include pictures, magnetic stripes, QR codes or barcodes for optical decoding, smart card chips, RFID, NFC, and personal details to help a security guard verify identity. Smart cards are credit card-sized IDs, badges, or security passes with an embedded magnetic stripe, barcode, or integrated circuit chip. They contain information about the authorized bearer that can be used for identification and/or authentication purposes. Some smart cards can even process information or store reasonable amounts of data in a memory chip. A smart card may be known by several phrases or terms. An identity token containing integrated circuits, ICs. A processor IC card. An IC card with an ISO 7816 interface, Figure 10.1. Smart cards are often viewed as a reliable security solution, but they should not be considered complete by themselves. Smart cards represent a something you have authentication factor. Like any single security mechanism, smart cards are subject to weaknesses and vulnerabilities. Smart cards can fall prey to physical attacks, logical attacks, Trojan horse attacks, or social engineering attacks. In most cases, a smart card is used in a multi-factor configuration. Thus, theft or loss of a smart card does not result in easy impersonation. The most common form of multi-factor used in relation to a smart card is the requirement of a PIN. You'll find additional information about smart cards in Chapter 13, Managing Identity and Authentication. Smart cards can serve dual or multiple purposes, such as gaining access to a facility just by waving the card near a wall-mounted reader, or gaining access to a computer system by inserting the card into a reader, which is usually followed by a prompt for a personal identification number, PIN, or other authentication factor, that is, MFA. Magnetic stripe cards are machine-readable ID cards with a magnetic stripe. Like a credit card, debit card, or ATM card, magnetic stripe cards can retain a small amount of data but are unable to process data like a smart card. Magnetic stripe cards often function as a type of two-factor control. The card is something you have, and its PIN is something you know. However, magnetic stripe cards are easy to copy or duplicate and are insufficient for authentication purposes in a secure environment. A badge can be used either for identification or for authentication. When a badge is used for identification, it is swiped in a device, and then the badge owner must provide one or more authentication factors, such as a password, passphrase, or biological trait if a biometric device is used. When a badge is used for authentication, the badge owner provides an ID, username, and so on, and then swipes the badge to authenticate. When an employee is terminated or otherwise departs the organization, badges should be retrieved and destroyed as part of the offboarding process. Facility security may require that badges be worn in plain view by each authorized person. Badges should be designed with security features to minimize the ability of intruders to replicate or duplicate. Day passes and/or visitor badges should be clearly marked as such with bright colors for easy recognition from a distance, especially for escort-required visitors. Proximity devices. In addition to smart cards, proximity devices can be used to control physical access. A proximity device can be a passive device, a field-powered device, or a transponder. The proximity device is worn or held by the authorized bearer. When it passes near a proximity reader, the reader device is able to determine who the bearer is and whether they have authorized access. The passive proximity device has no active electronics. It is just a small magnet with specific properties, like anti-theft devices commonly found in or on retail product packaging. A passive device reflects or otherwise alters the electromagnetic EM field generated by the reader device. This alteration is detected by the reader device, which triggers the alarm, records a log event, or sends a notification. A field-powered proximity device has electronics that activate when the device enters the EM field that the reader generates. Such devices actually generate electricity from an EM field to power themselves, such as card readers that require only that the access card be waved within inches of the reader to unlock doors. This is effectively the concept of radio frequency identification, RFID. See Chapter 11, Secure Network Architecture and Components, for more. A transponder proximity device is self-powered and transmits a signal received by the reader. This can occur consistently or only at the press of a button, like a garage door opener or car alarm key fob. Such devices may have batteries or capacitors, or may even be solar-powered. In addition to smart cards and proximity devices and readers, physical access can be managed with RFID or biometric access control devices. See Chapter 13 for a description of biometric devices. These and other devices, such as cable locks, locked rack-mount cabinets, and locks on data center doors, can support the protection and securing of equipment. Intrusion detection systems. Intrusion detection systems, IDSs, are systems, automated or manual, designed to detect an attempted physical intrusion, breach, or attack. The use of an unauthorized entry/point, or the occurrence of some specific event at an unauthorized or abnormal time. Intrusion detection systems used to monitor physical activity may include security guards, automated access controls, and motion detectors, as well as other specialty monitoring techniques. See Chapter 17, Preventing and Responding to Incidents, for a discussion of the different type of IDS that is a logical/technical control related to network or host breaches. Physical intrusion detection systems, also called burglar alarms, detect unauthorized activities and notify the authorities, internal security, or external law enforcement. The most common type of system uses a simple circuit dry contact switch at entrance points to detect when a door or window has been opened. Some windows may include an internal wire grid or a surface-mounted foil strip that detects when the glass has been broken. Some systems may even use a light beam-based tripwire mechanism to detect entry into a controlled area. This is similar to the safety mechanism located at the bottom of most automatic garage doors. All of these are examples of perimeter breach detection methods. Most IDS or burglar alarm systems will include both perimeter breach and internal motion detection methods, which in turn may trigger an authority response or an audible alarm. Two aspects of any intrusion detection and alarm system can cause it to fail: how it gets its power and how it communicates. If the system loses power, the detection and alarm mechanisms will not function. Thus, a reliable detection and alarm system has a battery backup with enough stored power for at least 24 hours of operation. If communication lines are cut, an alarm may not function, and security personnel and emergency services will not be notified. Thus, a reliable detection and alarm system incorporates a heartbeat sensor for line supervision. A heartbeat sensor is a mechanism by which the communication pathway is either constantly or periodically checked with a test signal. If the receiving station detects a failed heartbeat signal, such as the loss of the constant signal or missing one or two interval checks, the alarm triggers automatically. Both measures are designed to prevent intruders from circumventing the detection and alarm system by cutting power, cutting communication cables, or jamming radio signals. Motion detectors. A motion detector, or motion sensor, is a device that senses movement or sound in a specific area, and it is a common element of intruder detection systems. Many types of motion detectors exist, including the following. A digital motion detector monitors for significant or meaningful changes in the digital pattern of a monitored area. This is effectively a smart security camera. A passive infrared, PIR, or heat-based motion detector monitors for significant or meaningful changes in the heat levels and patterns in a monitored area. A wave pattern motion detector transmits a consistent low ultrasonic or high microwave frequency signal into a monitored area and monitors for significant or meaningful changes or disturbances in the reflected pattern. A capacitance motion detector senses changes in the electrical or magnetic field surrounding a monitored object. A photoelectric motion detector senses changes in visible light levels for the monitored area. Photoelectric motion detectors are usually deployed in internal rooms that have no windows and that are kept dark. A passive audio motion detector listens for abnormal sounds in the monitored area. Intrusion alarms. Whenever a motion detector registers a significant or meaningful change in the environment, it triggers an alarm. An alarm is a separate mechanism that triggers a deterrent, a repellent, and/or a notification. Deterrent alarms. Alarms that trigger deterrents may engage additional locks, shut doors, and so on. The goal of such an alarm is to make further intrusion or attack more difficult. Repellent alarms. Alarms that trigger repellents usually sound an audio siren or bell and turn on lights. These kinds of alarms are used to discourage intruders or attackers from continuing their malicious or trespassing activities and force them off the premises. Notification alarms. Alarms that trigger notifications are often silent from the intruder/attacker perspective, but record data about the incident and notify administrators, security guards, and law enforcement. A recording of an incident can take the form of log files and/or security camera recordings. The purpose of a silent alarm is to bring authorized security personnel to the location of the intrusion or attack in hopes of catching the person or persons committing the unwanted or unauthorized acts. Alarms are also categorized by where they are located: local, centralized or proprietary, or auxiliary. Local alarm system. Local alarm systems must broadcast an audible, up to 120 decibels alarm signal that can be easily heard up to 400 feet away. Additionally, they must be protected from tampering and disablement, usually by security guards. For a local alarm system to be effective, a security team or guards must be positioned nearby who can respond when the alarm is triggered. Central Station System. The alarm is usually silent locally, but off-site monitoring agents are notified so that they can respond to the security breach. Most residential security systems are of this type. Most central station systems are well-known or national security companies, such as Brinks and ADT. A proprietary system is similar to a central station system, but the host organization has its own on-site security staff waiting to respond to security breaches. Auxiliary alarm system. Auxiliary alarm systems can be added to either local or centralized alarm systems. When the security perimeter is breached, emergency services are notified to respond to the incident and arrive at the location. This can include fire, police, and medical services. Two or more of these types of intrusion and alarm systems can be incorporated in a single solution. Secondary verification mechanisms. When motion detectors, sensors, and alarms are used, secondary verification mechanisms should be in place. As the sensitivity of these devices increases, false triggers occur more often. Innocuous events, such as the presence of animals, birds, bugs, or authorized personnel, can trigger false alarms. Deploying two or more detection and sensor systems and requiring two or more triggers in quick succession to occur before an alarm is issued may significantly reduce false alarms and increase the likelihood that alarms indicate actual intrusions or attacks. Security cameras are security mechanisms related to motion detectors, sensors, and alarms. However, a security camera is not an automated detection and response system. A security camera usually requires personnel to watch the captured or live video to detect suspicious and malicious activities and to trigger alarms. Security cameras can expand the effective visible range of a security guard, therefore increasing the scope of the oversight. In many cases, a security camera is not used as a primary detection tool because of the high cost of paying a person to sit and watch the video screens. Instead, it is used as a secondary or follow-up mechanism that is reviewed after a trigger from an automated system occurs. In fact, the same logic used for auditing and audit trails is used for a security camera and recorded events. A security camera is a deterrent measure, whereas reviewing recorded events is a detective measure. Cameras. Video surveillance, video monitoring, closed-circuit television, CCTV, and security cameras are all means to deter unwanted activity and create a digital record of the occurrence of events. Cameras should be positioned to watch exit and entry points, allowing any change in authorization or access level. Cameras should also be used to monitor activities around valuable assets and resources, as well as to provide additional protection in public areas, such as parking structures and walkways. Tip: Closed-circuit television, CCTV, is a security camera system that resides inside an organization's facility and is usually connected to monitors for the security guards to view as well as to a recording device. Most traditional CCTV systems have been replaced by remote-controlled IP cameras, aka security cameras. Be sure the locations and capabilities of the security cameras are coordinated with the interior and exterior design of the facility. Cameras should be positioned to have clear sight lines of all exterior walls, entrance and exit points, and interior hallways. Security cameras can be overt and obvious in order to provide a deterrent benefit, or hidden and concealed in order to primarily provide a detective benefit. Most security cameras record to local or cloud-based storage. Cameras vary in type, including visible light, infrared, and motion-triggered recording. Some cameras are fixed, whereas others support remote control of automated pan, tilt, and zoom, PTZ. Some camera systems include a system on a chip, SoC, or embedded components, and may be able to perform various specialty functions, such as time-lapse recording, tracking, facial recognition, object detection, or infrared or color-filtered recording. Such devices may be targeted by attackers, infected by malware, or remotely controlled by malicious hackers. Dummy or decoy cameras can provide deterrence with minimal expense. Many security cameras are network connectable, that is, IP cameras, which allows them to be accessed and controlled over a network. Some cameras or enhanced video surveillance, EVS systems, are capable of object detection, which can include faces, devices, and weapons. Detection of an object or person could trigger retention of video, notification of security personnel, closing/locking doors, and/or sounding an alarm. Some cameras are activated through motion recognition. Motion recognition can trigger a retention of video and/or notify security personnel of the event. Some EVSs can even automatically identify individuals and track their motion across the monitored area. This may include gait analysis. Gait analysis is the evaluation of the way someone walks as a form of biometric authentication or identification. Each person has a unique walking pattern which can be used to recognize them. Gait analysis can be used for walking approach authentication as well as intrusion detection. Gait analysis is effectively a biological characteristic that can be used to differentiate between authorized individuals and unauthorized intruders. Simple motion recognition or motion-triggered cameras may be fooled by animals, birds, insects, weather, or foliage. In order to distinguish between a false alarm and an intrusion, a secondary verification mechanism should be used. Many camera solutions and EVSs can be enhanced using machine learning to improve video monitoring through automation, improved image recognition, and pattern/activity interpretation. Access abuses. No matter what form of physical access control is used, a security guard or other monitoring system must be deployed to prevent abuse, such as gaining unauthorized entry. Examples of access abuses of physical access controls include propping open secured doors or fail-safe exits and bypassing locks or access controls. Impersonation and masquerading are using someone else's security ID to gain entry into a facility. Tailgating and piggybacking are means to gain unauthorized entry by exploiting an authorized person. See Chapter 2, Personnel Security and Risk Management Concepts, for a discussion of impersonation, masquerading, tailgating, and piggybacking. Detecting abuses like these can be done by creating audit trails, retaining access log, using security cameras, and using security guards. Audit trails and access logs are useful tools even for physical access control. They may need to be created manually by security guards, or they can be generated automatically if sufficient automated access control mechanisms, such as smart cards and certain proximity devices, are in use. The time at which a subject requests entry, the result of the authentication process, and the length of time the secured gate remains open are important elements to include in audit trails and access logs. In addition to using the electronic or paper trail, consider monitoring entry points with security cameras that enable the comparison of the audit trails and access logs with a visual recording of the events. Such information is critical to reconstruct the events for an intrusion, breach, or attack. Media storage facilities. Media storage facilities should be designed to securely store blank media, reusable media, and installation media. Whether hard drives, flash memory drives, optical discs, or tapes, media should be protected against theft and corruption. A locked storage cabinet or closet should be sufficient for this purpose, but a safe can be installed if deemed necessary. New blank media should be secured to prevent someone from stealing it or planting malware on it. Media that is reused, such as thumb drives, flash memory cards, or portable hard drives, should be protected against theft and data remnant recovery. Data remnants are the remaining data elements left on a storage device after an insufficient sanitization process is used. Standard deletion or formatting processes clear out the directory structure and mark clusters as available for use, but leave the original data in the clusters. A simple undeletion utility or data recovery scanner can often recover access to these files. Restricting access to media and using secure wiping solutions can reduce this risk. Installation media need to be protected against theft and malware planting. This will ensure that when a new installation needs to be performed, the media is available and safe for use. Here are some means of implementing secure media storage facilities. Store media in a locked cabinet or safe rather than an office supply shelf. Have a media librarian or custodian who manages access to the locked media cabinet. Use a check-in/checkout process to track who retrieves, uses, and returns media from storage. For reusable media, when the device is returned, run a secure drive sanitization or zeroization, a procedure that erases data by replacing it with meaningless data such as zeros process to remove all data remnants. Media can also be verified using a hash-based integrity check mechanism to ensure either that valid files remain valid or that a medium has been properly and fully sanitized to retain no remnants of previous use. Tip: a safe is a movable secured container that is not integrated into a building's construction. A vault is a permanent safe or strong room that is integrated into a building's construction. For more security-intensive organizations, it may be necessary to place a security notification label on media to indicate its use classification, or employ RFID/NFC asset tracking tags on media. Higher levels of protection could also include fire, flood, electromagnetic field, and temperature monitoring and protection. Evidence storage. Evidence storage is quickly becoming a necessity for all businesses, not just law enforcement-related organizations. A key part of incident response is to gather evidence to perform root cause analysis. As cybercrime events continue to increase, it is important to retain logs, audit trails, and other records of digital events. It may also be necessary to retain image copies of drives or snapshots of virtual machines for future comparison. This may be related to internal corporate investigations or to law enforcement-based forensic analysis. In either case, preserving data sets that might be used as evidence is essential to the favorable conclusion to a corporate internal investigation or a law enforcement investigation of cybercrime. Secure evidence storage is likely to involve the following: using a dedicated storage system distinct from the production network, potentially keeping the storage system offline when not actively having new data sets transferred to it, blocking internet connectivity to and from the storage system, tracking all activities on the evidence storage system, calculating hashes for all data sets stored on the system, limiting access to the security administrator and legal counsel, encrypting all data sets stored on the system. There may be additional security requirements for an evidence storage solution based on your local regulations, industry, or contractual obligations. See Chapter 19, Investigations and Ethics, for more. Restricted and work area security. The design and configuration of internal security, including work areas and visitor areas, should be considered carefully. There should not be equal access to all locations within a facility. Areas that contain assets of higher value or importance should have more restricted access. For example, anyone who enters the facility should be able to access the restrooms and the public telephone without going into sensitive areas, and only network administrators and security staff should have access to the server room and wiring closets. Valuable and confidential assets should be located in the heart or center of protection provided by a facility. In effect, you should focus on deploying concentric circles of physical protection. This type of configuration requires increased levels of authorization to gain access into more sensitive areas inside the facility. Walls or partitions can be used to separate similar but distinct work areas. Such divisions deter casual shoulder surfing or eavesdropping. Shoulder surfing is the act of gathering information from a system by observing the monitor or the use of the keyboard by the operator. Floor-to-ceiling walls should be used to separate areas with differing levels of sensitivity and confidentiality. Where false or suspended ceilings are present, walls should cut these off as well, to provide an unbroken physical barrier between more and less secure areas. A clean desk policy or clean desk space policy is used to instruct workers how and why to clean off their desks at the end of each work period. In relation to security, such a policy has a primary goal of reducing disclosure of sensitive information. This can include passwords, financial records, medical information, sensitive plans or schedules, and other confidential materials. If at the end of each day/shift, a worker places all work materials into a lockable desk drawer or file cabinet, this prevents exposure, loss, and/or theft of these materials. Each work area should be evaluated and assigned a classification, just as IT assets are classified. Only people with clearance or classifications corresponding to the classification of the work area should be allowed access. Areas with different purposes or uses should be assigned different levels of access or restrictions. The more access to assets the equipment within an area offers, the more important the restrictions become that are used to control who enters those areas and what activities they are allowed to perform. Your facility security design process should support the implementation and operation of internal security. In addition to the management of workers in proper workspaces, you should address visitors and visitor control. Should there be an escort requirement for visitors, and what other forms of visitor control should be implemented? In addition to basic physical security tools such as keys and locks, mechanisms such as access control vestibules, video cameras, written logs, security guards, and RFID ID tags should be implemented. An example of a secure or restricted work area is the Sensitive Compartmented Information Facility, SCIF. A SCIF is often used by government and military agencies, divisions, and contractors to provide a secure environment for highly sensitive data storage and computation. The purpose of a SCIF is to store, view, and update sensitive compartmented information, SCI, which is a type of classified information. A SCIF has restricted access to limit entrance to those individuals with a specific business need and authorization to access the data contained within. This is usually determined by the individual's clearance level and SCI approval level. In most cases, a SCIF has restrictions against using or possessing photography, video, or other recording devices while in the secured area. A SCIF can be established in a ground-based facility, an aircraft, or a floating platform. A SCIF can be a permanent installation or a temporary establishment, and it is typically located within a structure, although an entire structure can be implemented as a SCIF. Utility considerations. Reliable operations of IT and continued ability to perform business tasks often depend on consistency in the mundane utilities. The following sections discuss security concerns of power, noise, temperature, and humidity. Power considerations. Power supplied by electric companies is not always consistent and clean. Most electronic equipment demands clean power to function properly. Equipment damage from power fluctuations is a common occurrence. Many organizations opt to manage their own power through various means. The first stage or level of power management is using surge protectors. However, these only offer protection against power overloads. In the event a spike of power occurs, the surge protector's fuse will trip or blow, that is, burn out, and all power will be cut off. Surge protectors should be used only when instant termination of electricity will not cause damage or loss to the equipment. The next level is to use a power conditioner or power line conditioner. It is a form of advanced surge protector that is also able to remove or filter line noise. The third level of power protection is to use an uninterruptible power supply, UPS. A UPS is a type of self-charging battery that can be used to supply consistent, clean power to sensitive equipment. Most UPS devices provide surge protection and power conditioning in addition to battery-supplied supplemental power. There are two main types of UPSs: double conversion and line interactive. A UPS can also be called a backup UPS or a standby UPS. A double conversion UPS functions by taking power in from the wall outlet, storing it in a battery, pulling power out of the battery, and then feeding that power to whatever devices are connected to it. By directing current through its battery, it is able to maintain a consistent clean power supply to whatever devices are connected to it. A line interactive UPS has a surge protector, battery charger/inverter, and voltage regulator positioned between the grid power source and the equipment. The battery is not in line under normal conditions. There is a type of three-position switch that, if the grid fails, will automatically switch so that power is pulled from the battery through the inverter and voltage regulator to provide power to the equipment. Lower quality versions of this type of UPS may have a very short moment when power is interrupted. Although most systems should be able to continue operating with this fault, it can be damaging to sensitive devices or cause other equipment to shut down and/or reboot. The primary purpose of a UPS is the battery-supplied power that can continue to support the operating of electrical devices in the event of power loss or a disconnect from the power grid. A UPS can continue to supply power for minutes or hours, depending on its battery capacity and how much power the equipment attached to it needs. That is, the load placed on it. When designing a UPS-based power management solution, consider what systems are critical and thus need continued power versus those that can be allowed to be powered off during any loss of power. This approach can assist with optimization and distribution of critical power reserves. Another power option is that of the battery backup or failover battery. This is a system that collects power into a battery but can switch over to pulling power from the battery when the power grid fails. Generally, this type of system was implemented to supply power to an entire building rather than just one or a few devices. Many traditional versions of battery backups were not implemented as a form of UPS, and thus there was usually a period of time, even if just a moment of complete power loss to the equipment, as the grid source of power fails and a switching event occurs to retrieve power from a battery. Some modern battery backups are implemented more like a UPS, so that there is no interruption of power. The highest level of power protection is the use of generators. If maintaining operations for a considerable time in spite of a brownout or blackout is a necessity, on-site electric generators are required. Such generators turn on automatically when a power failure is detected. Most generators operate using a fuel tank of liquid or gaseous propellant that must be maintained to ensure reliability. Electric generators are considered alternate or backup power sources. With sufficient supply of fuel, especially if resupply is possible, then a power generator can serve as an alternative power source for a long period of time. UPSs should still be used even when a generator is installed to provide continuous alternative power. The purpose of the UPS in this situation is to provide power long enough to complete a logical shutdown of a system or until a generator is powered on and providing stable power. It may take a generator several minutes before it is triggered, starts, that is, turns on, and is warmed up in order to provide consistent power. Ideally, power is consistently clean without any fluctuations. But in reality, commercial power suffers from a wide assortment of problems. Here is a list of terms associated with power issues you should know. Fault, a momentary loss of power. Blackout, a complete loss of power. Sag, momentary low voltage. Brownout, prolonged low voltage. Spike, momentary high voltage. Surge, prolonged high voltage. Inrush, an initial surge of power usually associated with connecting to a power source, whether primary or alternate/secondary. Ground, the wire in an electrical circuit that provides an alternate pathway for electricity to flow to the earth, that is, the ground. All of these issues can cause problems for electrical equipment. When experiencing a power issue, it is important to determine where the fault is occurring. If the issue takes place outside your meter, then it is to be repaired by the power company, whereas any internal issues are your responsibility. Noise. Noise is the interference of power through some form of disturbance, interruption, or fluctuation. Noise that is not consistent is labeled as transient noise. Noise can cause more than just problems with how equipment functions related to its power source. It can also interfere with the quality of communications, transmissions, and playback. Noise generated by electric current can affect any means of data transmission that relies on electromagnetic transport mechanisms, such as telephone, cellular, television, audio, radio and network mechanisms. There are two types of electromagnetic interference, EMI: common mode and traverse mode. Common mode noise is generated by a difference in power between the hot and ground wires of a power source or operating electrical equipment. Traverse mode noise is generated by a difference in power between the hot and neutral wires of a power source or operating electrical equipment. Radio frequency interference, RFI, is another source of noise and interference that can affect many of the same systems as EMI. A wide range of common electrical appliances generate RFI, including fluorescent lights, electrical cables, electric space heaters, computers, elevators, motors, and electric magnets. So it's important to locate all such equipment when deploying IT systems and infrastructure elements. Protecting your power supply and your equipment from noise is an important part of maintaining a productive and functioning environment for your IT infrastructure. Steps to take for this kind of protection include providing for sufficient power conditioning, establishing proper grounding, using shielded cables, running cables through shielding conduits, switching to fiber optic cables for networking, and limiting copper cable exposure to EMI and RFI sources. Temperature, humidity, and static. In addition to power considerations, maintaining the environment involves control over the HVAC mechanisms. Rooms intended primarily to house computers should generally be kept between 59 and 89.6 degrees Fahrenheit, 15 and 32 degrees Celsius. Source: energy-350.com/ASHRAE-releases-new-data-center-standards. However, there are some extreme environments that run their equipment 10 to 20 degrees Fahrenheit lower or higher than this range. The actual temperature is not as important as keeping devices from reaching a temperature that would cause damage and optimizing temperature related to device performance and humidity management. Some devices may operate more efficiently at higher or lower temperatures. Generally, temperature management is optimized using fans, either directly connected to heat sinks on devices like CPUs, memory banks, or video cards, or indirectly by being part of their chassis or host storage cabinet, such as a rack mount cabinet. Fans are used to pull warm/hot air off equipment and out of devices and allow it to be replaced by cooler air. Hot and cold aisles are a means of maintaining optimum operating temperature in large server rooms. The overall technique is to arrange server racks in lines separated by aisles, figure 10.2. Then, the airflow system is designed so hot, rising air is captured by air intake vents on the ceiling, whereas cold air is returned in opposing aisles from either the ceiling or the floor. Thus, every other aisle is hot, then cold. Tip: a common HVAC-related term is plenum. The plenum consists of boxes and tubes that distribute conditioned air throughout a building. Plenum spaces are the areas of a building designed to contain the HVAC plenum components. Plenum spaces are typically distinct and separate from human inhabitable spaces within a building. Due to building codes in most countries, anything that is placed into the plenum space must be plenum-related. This is a type of fire rating requiring that those products produce minimal levels of smoke and/or toxic gases, especially if the building has enclosed spaces that could trap gases. Electrical cables and networking cables are common plenum-rated products. A related important aspect of temperature management is to attempt to maintain a stable temperature rather than allow the temperature to fluctuate up and down. Such heat oscillations can cause expansion and contraction of materials. This could cause chip creep, where friction fit connections work their way out of their sockets, or cracks in soldered connections. We also recommend that you maintain positive air pressure in the data center, as well as superior levels of air filtration. These efforts will help reduce the infiltration of dust, debris, microfine particulate matter, and other contaminants, such as cleaning chemicals or vehicle exhaust. Without such efforts, these unwanted particles can build up over time. Dust bunnies can attach to surfaces due to static charges or may cause corrosion. Additionally, humidity in a computer room should be maintained between 20 and 80%. Source: energy350.com/ASHRAE-new-data-center-standards. Too much humidity can result in condensation, which causes corrosion. Too little humidity allows for static electricity buildup, which can result in electrostatic discharge, ESD. Even with anti-static carpeting, if the environment has low humidity, it is still possible to generate 20,000-volt static discharges from your human body via ESD. Table 10.1 shows that even minimal levels of static discharge can destroy electronic equipment. Table 10.1. Static voltage and damage. Static voltage 40. Possible damage: destruction of sensitive circuits and other electronic components. Static voltage 1000. Possible damage: scrambling of monitor displays. Static voltage 1500. Possible damage: destruction of data stored on hard drives. Static voltage 2000. Possible damage: abrupt system shutdown. Static voltage 4000. Possible damage: printer jam or component damage. Static voltage 17,000. Possible damage: permanent circuit damage. Tip: environmental monitoring is the process of measuring and evaluating the quality of the environment within a given structure. This can focus on general or basic concerns such as temperature, humidity, dust, smoke, and other debris. However, more advanced systems can include chemical, biological, radiological, and microbiological detectors. Water issues. Water issues, such as leakage and flooding, should be addressed in your environmental safety policy and procedures. Plumbing leaks are not an everyday occurrence, but when they do happen, they can cause significant damage. Water and electricity don't mix. If your computer systems come into contact with water, especially while they are operating, damage is sure to occur. Plus, water and electricity create a serious risk of electrocution for nearby personnel. Whenever possible, locate server rooms, data centers, and critical computer equipment away from any water source or transport pipes located in the building. You may also want to install water detection circuits on the floor or under the floor with raised flooring data centers around mission-critical systems. Water detection circuits will sound an alarm and alert you if water is encroaching upon the equipment. To minimize emergencies, be familiar with shut-off valves and drainage locations. In addition to monitoring for plumbing leaks, you should evaluate your facility's ability to handle severe rain or flooding in its vicinity. Is the facility located on a hill or in a valley? Is there sufficient drainage? Is there a history of flooding or accumulation of standing water? Is a server room in the basement or on the first floor? Are there water features or landscaping around the building that might cause flooding or direct heavy rainfall toward and into the building? Fire prevention, detection, and suppression. Fire prevention, detection, and suppression must not be overlooked. Protecting personnel from harm should always be the most important goal of any security or protection system. In addition to protecting people, fire detection and suppression is designed to keep asset damage caused by fire, smoke, heat, and suppression materials to a minimum. Standard fire prevention and resolution training involves knowledge of the fire triangle. The three corners of the triangle represent fuel, heat, and oxygen. The center of the triangle represents the chemical reaction among these three elements. The purpose of the fire triangle is to illustrate that if you can remove any one of the four items from the fire triangle, the fire can be extinguished. Different suppression mediums address different aspects of the fire. Water suppresses the temperature. Soda acid and other dry powders suppress the fuel supply. Carbon dioxide, CO2, suppresses the oxygen supply. Halon substitutes and other non-flammable gases interfere with the chemistry of combustion and/or suppress the oxygen supply. When selecting a suppression medium, consider what aspect of the fire triangle it addresses, what this really represents, how effective the suppression medium usually is, and what impact the suppression medium will exert on your environment. In addition to understanding the fire triangle, you should understand the stages of fire. Fires go through numerous stages, and Figure 10.4 addresses the four most vital stages. Stage 1, the incipient stage. At this stage, there is only air ionization and no smoke. Stage 2, the smoke stage. In Stage 2, smoke is visible from the point of ignition. Stage 3, the flame stage. This is when a flame can be seen with the naked eye. Stage 4, the heat stage. At Stage 4, the fire is considerably further down the time scale to the point where there is an intense heat buildup and everything in the area burns. The earlier a fire is detected, the easier it is to extinguish and the less damage it and its suppression medium or mediums can cause. One of the basics of fire management is proper personnel awareness training. Employees need to be trained in safety and escape procedures. Everyone should be thoroughly familiar with the fire suppression mechanisms in their facility. Everyone should also be familiar with at least 2 evacuation routes from their primary work area and know how to locate evacuation routes elsewhere in the facility. Typically, evacuation routes are indicated by emergency exit signs, illustrated by maps posted on walls and located in common or central areas such as near elevators, and defined in personnel training and reference manuals. Personnel should be trained in the location and use of fire extinguishers. Other items to include in fire or general emergency response training include cardiopulmonary resuscitation, CPR, emergency shutdown procedures, general first aid, automated external defibrillator AED devices, and a pre-established rendezvous location or safety verification mechanism, such as voicemail. Once employees are trained, their training should be tested using drills and simulations. All elements of physical security, especially those related to human life and safety, should be tested on a regular basis. It is mandated by law in the United States that fire extinguishers, fire detectors/alarms, and elevators be inspected regularly. Tip: most fires in a data center are caused by overloaded electrical distribution outlets. A second common cause is improper use of heating devices, such as coffee pots, hot plates, and space heaters, when located near combustible materials, such as paper, cloth, and cardboard. Fire extinguishers. If a worker notices a fire before it is detected by the building, then they may be able to use a handheld fire extinguisher to put out the fire. There are several types of fire extinguishers. Understanding what type to use on various forms of fire is essential to effective fire suppression. If a fire extinguisher is used improperly, or the wrong form of fire extinguisher is used, The fire could spread and intensify instead of being quenched. A fire extinguisher may be effective through the first 3 stages of fire, but is unlikely to be of any use at stage 4, the heat stage. Fortunately, local fire regulations and building codes typically dictate the type of fire extinguisher to be present. For most standard office environments, a multi-class extinguisher, likely an ABC, is deployed because it is suitable for the widest range of common fire types in that type of location. Table 10.2 lists common types of fire extinguishers. Table 10.2, Fire Extinguisher Classes. Class A. Type common combustibles. Suppression material, water, soda acid, a dry powder or liquid chemical. Class B. Type liquids. Suppression material, CO2, halon or alternate gas options, soda acid. Class C. Type electrical. Suppression material, CO2, halon or alternate gas options. Class D. Type metal. Suppression material, dry powder. Class K. Type cooking media, fats, grease, oil. Suppression material, alkaline mixtures, for example potassium acetate, potassium citrate, or potassium carbonate, to cause saponification. Tip: water and other liquids cannot be used on Class B/K fires because it would vaporize, causing a type of explosion and spreading the burning liquids all over the area. Water cannot be used on Class C fires because of the potential for electrocution. Oxygen suppression cannot be used on metal fires because burning metal produces its own oxygen. Fire detection systems. Properly protecting a facility from fire requires installing an automated detection and suppression system. There are many types of fire detection systems. Fixed temperature detection systems trigger suppression when a specific temperature is reached. This is the most common type of detector and present in most office buildings. The potentially visible sprinkler head serves as both the detection and release mechanism. The trigger is usually a metal or plastic component that is in the sprinkler head and melts at a specific temperature. There is also a version with a small glass vial containing chemicals that vaporize to overpressurize and shatter the container at a specific temperature. This system is inexpensive and very reliable, even over long periods of time. Rate of rise detection systems trigger suppression when the speed at which the temperature changes reaches a specific level. These are often digital temperature measuring devices which can be fooled by HVAC heating during winter months and thus are not widely deployed. Flame-actuated systems trigger suppression based on the infrared energy of flames. This mechanism is fast and reliable, but often fairly expensive. Thus, it is often only used in high-risk environments. Smoke-actuated systems use photoelectric or radioactive ionization sensors as triggers. Either method monitors for light or radiation obstruction or reduction across an air gap caused by particles in the air. It is intended to be triggered by smoke, but dust and steam can sometimes trigger the alarm. The radioactive ionization-based smoke detectors use americium as a source of alpha particles and a Geiger counter to detect the rate of these particles' transmission across the air gap. This element produces such low levels of radiation that a layer of dead skin cells is sufficient to block its transmission. Incipient smoke detection systems, also known as aspirating sensors, are able to detect the chemicals typically associated with the very early stages of combustion before a fire is otherwise detectable via other means. These devices are even more costly than flame-actuated sensors and are also only used in high-risk or critical environments. To be effective, fire detectors need to be placed strategically. Don't forget to place them inside dropped ceilings and raised floors, in server rooms, in private offices and public areas, in HVAC vents, in elevator shafts, in the basement, and so on. Once a fire detection device notices the presence of a fire, it typically will trigger the fire alarm. Most fire alarms are loud, piercing beeps or sirens paired with brightly flashing lights. A fire alarm is intended to be obvious, startling, and attention-grabbing. There is usually no mistaking a fire alarm or not noticing that it went off. Once a fire alarm occurs, all personnel should follow their safety training and begin to exit the building. Most fire detection systems can be linked to fire response service notification mechanisms. When suppression is triggered, such linked systems will contact the local fire response team and request aid using an automated message or alarm. As for fire suppression mechanisms, they can be based on a water or gas system. Water is common in human-friendly environments, whereas gaseous systems are more appropriate where personnel typically do not reside and generally non-human compatible areas. Water suppression systems. There are four main types of water suppression systems. A wet pipe system, also known as a closed-head system, is always full of water. Water discharges immediately when suppression is triggered. A dry pipe system contains compressed inert gas. Once suppression is triggered, the inert gas is released, opening a water valve that in turn causes the pipes to fill and discharge water into the environment moments later. A pre-action system is a variation of the dry pipe system that uses a two-stage detection and release mechanism. The system exists as a dry pipe until the initial stages of a fire, smoke, heat, and so on, are detected, and then the pipes are allowed to fill with water, stage 1. The water is released only after the sprinkler head activation triggers are triggered by sufficient heat, stage 2. If the fire is quenched before sprinklers are triggered, pipes can be manually emptied and reset. This also allows manual intervention, typically via a button mounted on a wall, to stop the release of water before sprinkler release occurs. A deluge system is a system that uses larger pipes and therefore delivers a significantly larger volume of water. Also, when one sprinkler head opens, they all open to fully deluge the area with suppressant. Deluge systems are inappropriate for environments that contain electronics and computers. Pre-action systems are the most appropriate water-based systems for environments that house both computers and humans together, because they provide the opportunity to prevent the release of water in the event of a false alarm or false initial trigger. Tip: the most common cause of failure for a water-based system is human error, such as turning off a water source when a fire occurs or triggering water release when there is no fire. Gas discharge systems. Gas discharge systems use a compressed gas to effectively extinguish fire. However, gas discharge systems should not be used in environments in which people are located. Gas discharge systems usually remove the oxygen from the air, thus making them hazardous to personnel. They employ a pressurized gaseous suppression medium, such as carbon dioxide, CO2, halon, or FM200, a halon replacement. Benefits of gas-based fire suppression include causing the least damage to computer systems, extinguishing the fire quickly by removing oxygen, and being more effective and faster than a water-based system. CO2 is an effective fire suppressant, but it poses a risk to people. If CO2 leaks into an enclosed space, it can cause asphyxiation at only a 7.5% concentration. Fire suppressant use of CO2 is often at 34% or higher concentration. CO2 is naturally colorless, odorless, and tasteless, So extreme care must be used when deploying a CO2 system. There are some additives available to induce an odor. Due to its risks, CO2 should be implemented only in special circumstances where personnel will not be present and a water-based system is inappropriate, such as engine compartments, generator rooms, around flammable liquids, and large industrial equipment. CO2 is able to reduce temperatures as well as keep oxygen away from combustion locations. Halon is an effective fire suppression compound. It starves a fire of oxygen by disrupting the chemical reaction of combustion, but it degrades into toxic gases at 900 degrees Fahrenheit. Also, it is not environmentally friendly. It is an ozone-depleting substance. The 1989 Montreal Protocol initiated the termination of manufacturing of ozone-depleting substances, which includes halon. In 1994, the EPA banned the manufacture of halon in the United States, as well as importing halon into the country. However, according to the Montreal Protocol, you can obtain halon by contacting a halon recycling facility. The EPA seeks to exhaust existing stocks of halon to take this substance out of circulation, although even in 2020, there are still significant domestic stockpiles of halon. Owing to issues with halon, it is often replaced by a more ecologically friendly and less toxic medium. There are dozens of EPA-approved substitutes for halon. For a complete list, see epa.gov/snap/substitutes-total-flooding-agents. You can also replace halon substitutes with low-pressure water mists, but such systems are usually not employed in computer rooms or electrical equipment storage facilities. A low-pressure water mist is a vapor cloud used to quickly reduce the temperature in an area. Damage. Addressing fire detection and suppression includes dealing with possible contamination and damage caused by a fire. The destructive elements of a fire include smoke and heat, but they also include the suppression media, such as water or soda acid. Smoke and soot are damaging to storage devices and many computer components. Heat can damage any electronic or computer component. For example, temperatures of 100 degrees Fahrenheit can damage storage tapes, 175 degrees can damage computer hardware, CPU and RAM, and 350 degrees can damage paper products through warping and discoloration. Suppression media can cause short circuits, initiate corrosion, or otherwise render equipment useless. All these issues must be addressed when designing a fire response system. Even a small fire might trigger the IRP, BCP, or DRP. Warning. Don't forget that in the event of a fire, in addition to damage caused by the flames and your chosen suppression medium, members of the fire department may inflict damage using their hoses to spray water and their axes while searching for people to rescue and locating hotspots. Implement and manage physical security. Many types of physical access control mechanisms can be deployed in an environment to control, monitor, and manage access to a facility. These range from deterrence to detection mechanisms. The various sections, divisions, or areas within a site or facility should be clearly designated as public, private, or restricted. Each of these areas requires unique and focused physical access controls, monitoring, and prevention mechanisms. The following sections discuss many such mechanisms that may be used to separate, isolate, and control access to various areas of a site, including perimeter and internal security. Signage or signs can be used to declare areas off-limits to those who are not authorized, indicate that security cameras are in use, and disclose safety warnings. Signs are useful in deterring minor criminal activity, establishing a basis for recording events, and guiding people into compliance or adherence with rules or safety precautions. Signs are usually physical displays with words or images, but digital signs and warning banners should be implemented as well on both local and remote connections. If not mandated by regulations, a self-imposed schedule of control testing should be implemented for door locks, fences, gates, access control vestibules, turnstiles, video cameras, and all other physical security controls. Perimeter security controls. The accessibility to the building or campus location is also important. Single entrances are great for providing security, but multiple entrances are better for evacuation during emergencies. What types of roads are nearby, such as residential streets or highways? What means of transportation are easily accessible? Trains, highway, airport, shipping? What about traffic levels throughout the day? Keep in mind that accessibility is also constrained by the need for perimeter security. The needs of access and use should meld and support the implementation and operation of perimeter security. The use of physical access controls and monitoring personnel and equipment entering and leaving, as well as auditing/logging all physical events, are key elements in maintaining overall organizational security. Fences, gates, turnstiles, and access control vestibules. A fence is a perimeter-defining device. Fences are used to clearly differentiate between areas that are under a specific level of security protection and those that aren't. Fencing can include a wide range of components, materials, and construction methods. It can consist of stripes painted on the ground, chain link fences, barbed wire, concrete walls, and even invisible perimeters using laser, motion, or heat detectors. Various types of fences are effective against different types of intruders. Fences 3 to 4 feet high deter casual trespassers. Fences 6 to 7 feet high are too hard to climb easily and deter most intruders except determined ones. Fences 8 or more feet high with strands of barbed or razor wire deter even determined intruders. An advanced form of fencing is known as a Perimeter Intrusion Detection and Assessment System, PIDAS. A PIDAS is a fence system that has 2 or 3 fences used in concert to optimize security. PIDAS fencing is often present around military locations and prisons. Typically, a PIDAS fence has one main tall fence that may be 8 to 20 feet tall. The main fence may be electrified, may have barbed wire/razor wire elements, and or can include touch detection technologies. This main fence is then surrounded by an outside fence, which may only be 4 to 6 feet tall. The purpose of this outer fence is to keep animals and casual trespassers from accessing the main fence. This reduces the nuisance alarm rate, NAR, or false positives from animals or foliage on interior fences. Additional fences can be located between the main fence and the exterior fence. These additional fences may be electrified or use barbed/razor wire. The space between the fences can serve as a corridor for guard patrols or wandering guard dogs. These corridors are kept free of vegetation. A gate is a controlled exit and entry point in a fence or wall. The deterrent level of a gate must be equivalent to the deterrent level of the fence to sustain the effectiveness of the fence as a whole. Hinges and locking/closing mechanisms should be hardened against tampering, destruction, or removal. When a gate is closed, it should not offer any additional access vulnerabilities. Keep the number of gates to a minimum. They can be monitored by guards. When they're not protected by guards, use of dogs or security cameras is recommended. A turnstile is a form of gate that prevents more than one person at a time from gaining entry and often restricts movement in one direction. It is used to gain entry but not to exit, or vice versa. A turnstile is basically the fencing equivalent of a secured revolving door. A turnstile can be designed to turn freely to allow easy egress. An ingress turnstile can be implemented with a locking mechanism that requires personnel to provide a code, combination, or credential before it will allow a single person to enter the secured area. A turnstile can be used as a personnel flow control device to limit the direction of travel and the speed of access. That is, only one person can pass at a time after valid authentication. An access control vestibule, also known as a man-trap, is a double set of doors, also shown in Figure 10.5, that is often protected by a guard or some other physical layout that prevents piggybacking and can trap individuals at the discretion of security personnel. The purpose of an access control vestibule is to immobilize a subject until their identity and authentication authority are verified. If a subject is authorized for entry, the inner door opens, allowing entry into the facility or onto the premises. If a subject is not authorized, both doors remain closed and locked until an escort, typically a guard or a police officer, arrives to escort the subject off the property or arrest the subject for trespassing. This is known as a delay feature. Often, an access control vestibule includes a scale to prevent piggybacking or tailgating. Access control vestibules can be used to control entrance into a facility or entrance within a facility to a higher secured area, such as a data center or a SCIF. Another key element of physical security, especially for data centers, government facilities, and highly secure organizations, is security bollards, which prevent vehicles from ramming access points and entrances. These can be permanently fixed in place or automatically rise from their installed base at a fixed time or an alert. They are often disguised as planters or other architectural elements. See the previous discussion of CPTED in the Facility Design section. Barricades, in addition to fencing, are used to control both foot traffic and vehicles. K-rails, often seen during road construction, large planters, zigzag queues, bollards, and tire shredders are all examples of barricades. When used properly, they can control crowds and prevent vehicles from being used to cause damage to your building. Long, straight, and unobstructed vehicle paths should be avoided in order to prevent the buildup of excessive speed. If generators and fuel storage are present, additional layers of barricade protection may be necessary to prevent tampering or destruction. Lighting. Lighting is the most commonly used form of perimeter security control, providing the security benefit of deterrence. The primary purpose of lighting is to discourage casual intruders, trespassers, prowlers, or would-be thieves who would rather perform their misdeeds, such as vandalism, theft, and loitering, in the dark. Both interior and exterior lighting should be implemented for security, especially related to parking areas, walkways, and entrances. Exterior lighting should generally be on from dusk until dawn. Interior lighting may be always on, switched manually, or triggered on demand, possibly via motion. Emergency lighting should be implemented in key areas, such as exits and escape routes, and triggered with the loss of power or along with a fire alarm. Lighting is often claimed to be the most commonly deployed physical security mechanism. However, lighting is only a deterrent and not a strong deterrent. It should not be used as the primary or sole protection mechanism except in areas with a low threat level. Your entire site, inside and out, should be well lit. This provides for easy identification of personnel and makes it easier to notice intrusions. Lighting should not necessarily be used to illuminate the positions of guards, dogs, patrol posts, or other similar security elements. However, these can be illuminated if knowledge of their presence is to be used as a deterrent. Lighting should be combined with security guards, guard dogs, security cameras, or some other form of intrusion detection or surveillance mechanism. Lighting must not cause a nuisance or problem for nearby residents, roads, railways, airports, and so on. It should also never cause glare or reflective distraction to guards, dogs, and monitoring equipment, which could otherwise aid attackers during break-in attempts. Strong lights used to illuminate a building located on a fence line pointing inward can function as a means to hide intruders. Just think of standing in the dark with someone pointing a flashlight at you. You will be unable to see them because the light overpowers your vision. It is generally accepted as a de facto standard that lighting used for perimeter protection should illuminate critical areas with at least 2 foot candles of power, which is approximately 2 lumens or 20 lux. Another common issue for the use of lighting is the placement of the lights. Standards seem to indicate that light poles should be placed the same distance apart as the diameter of the illuminated area created by illumination elements. Thus, if a lighted area is 40 feet in diameter, poles should be 40 feet apart. This light pole positioning allows for the intersection of lighted areas on the ground, thus preventing an intruder to gain access under the cover of darkness. Security guards and guard dogs. All physical security controls, whether static deterrence or active detection and surveillance mechanisms, ultimately rely on personnel to intervene and stop actual intrusions and attacks. Security guards exist to fulfill this need. Guards can be posted around a perimeter or inside to monitor access points or watch detection and surveillance monitors. The real benefit of guards is that they are able to adapt and react to various conditions or situations. Guards can learn and recognize attack and intrusion activities and patterns, can adjust to a changing environment, and can make decisions and judgment calls. Security guards are often an appropriate security control when immediate situation handling and decision-making on site is necessary. Guards should perform patrols both internally and externally to look for security violations, unauthorized entities, or other abnormalities throughout the facility and campus grounds. Patrols should be frequent, but at random intervals. This prevents an intruder from observing a pattern of patrols and then timing their break-in accordingly. Unfortunately, using security guards is not a perfect solution. There are numerous disadvantages to deploying, maintaining, and relying on security guards. Not all environments and facilities support security guards. This may be because of actual human incompatibility or the layout, design, location, and construction of the facility. Not all security guards are themselves reliable. Pre-screening, bonding, and training do not guarantee that you won't end up with an ineffective or unreliable security guard. Even if a guard is initially reliable, guards are subject to physical injury and illness, take vacations, can become distracted, are vulnerable to social engineering, and may become unemployable because of substance abuse. In addition, security guards usually offer protection only up to the point at which their life is endangered. Additionally, security guards are usually unaware of the scope of the operations within a facility and are therefore not thoroughly equipped to know how to respond to every situation. Though this is considered a disadvantage, the lack of knowledge of the scope of the operations within a facility can also be considered an advantage, because this supports confidentiality of those operations and thus helps reduce the possibility that a security guard will be involved in the disclosure of confidential information. Finally, security guards are expensive, whether they are employees or provided by a third-party contractor. Guard dogs can be an alternative to security guards. They can often be deployed as a perimeter security control. As a detection and deterrent, dogs are extremely effective. However, dogs are costly, require a high level of maintenance, and impose serious insurance and liability requirements. Robot sentries can be used to automatically patrol an area to look for anything out of place. Robot sentries often use facial recognition to identify authorized individuals as well as potentially identify intruders. Robot sentries can be on wheels or be a type of drone. Internal security controls. If a facility is designed with restricted areas to control physical security, a mechanism to handle visitors is required. Often, an escort is assigned to visitors, and their access and activities are monitored closely. Failing to track the actions of outsiders when they are allowed into a protected area can result in malicious activity against the most protected assets. Visitor control can also benefit from the use of keys, combination locks, badges, motion detectors, intrusion alarms, and more. Reception can be used as a choke point to block access to unauthorized visitors. The reception area should be segregated from the security areas with locked doors and monitored by security cameras. If a visitor is authorized, then an escort can be assigned to accompany them around the facility. If a valid worker arrives, the receptionist may be able to buzz the door open for them. Any unauthorized visitors can be asked to leave, security guards can be brought to bear, or police can be called. Visitor logs are a manual or automated list of non-employee entries or access to a facility or location. Employee logs may also be useful for access tracking and verification. Logs of physical access should be maintained. These can be created automatically through the use of smart cards or manually by a security guard. The physical access logs establish context for the interpretation of logical logs. Logs are helpful in an emergency to determine whether everyone has escaped a building safely. Keys and combination locks. Locks keep closed doors closed. They are designed and deployed to prevent access to everyone without proper authorization. A lock is a crude form of an identification and authorization mechanism. If you possess the correct key or combination, you are considered authorized and permitted entry. Key-based locks are the most common and inexpensive forms of physical access control devices. These are often known as preset locks, deadbolt locks, or conventional locks. These types of locks are subject to lock picking, which is often categorized under a class of lock mechanism attacks called shimming. Many conventional locks are also vulnerable to an attack known as bumping. Bumping is accomplished using a special bump key that, when properly tapped or bumped, causes the lock pins to jump and allows the cylinder to turn. To see how these lock attacks are performed, watch videos from youtube.com/c/helpful-lock-picker and youtube.com/c/lock-picking-lawyer. Programmable or combination locks offer a broader range of control than preset locks. Some programmable locks can be configured with multiple valid access combinations, or may include digital or electronic controls employing keypads, smart cards, or cipher devices. For instance, an electronic access control, EAC lock, incorporates 3 elements: an electromagnet to keep the door closed, a credential reader to authenticate subjects and to disable the electromagnet, and a sensor to re-engage the electromagnet when the door is closed. An EAC can monitor the amount of time that a door stays open in order to trigger a warning buzzer if a door stays open for longer than 5 seconds, and trigger an intrusion alarm if the door stays open for longer than 10 seconds. Times are examples, not prescriptions. Locks serve as an alternative to security guards as a perimeter entrance access control device. A gate or door can be opened and closed to allow access by a security guard who verifies your identity before granting access, or the lock itself can serve as the verification device that also grants or restricts entry. Environment and life safety. An important aspect of physical access control and maintaining the security of a facility is protecting the basic elements of the environment and protecting human life. In all circumstances and under all conditions, the most important aspect of security is protecting people. Thus, preventing harm to people is the most important goal for all security solutions. Part of maintaining safety for personnel is maintaining the basic environment of a facility. For short periods of time, people can survive without water, food, air conditioning, and power. But in some cases, the loss of these elements can have disastrous results, or they can be symptoms of more immediate and dangerous problems. Flooding, fires, release of toxic materials, and natural disasters all threaten human life as well as the stability of a facility. Physical security procedures should focus on protecting human life, and then on restoring the safety of the environment and restoring the utilities necessary for the IT infrastructure to function. People should always be your top priority. Only after personnel are safe can you consider addressing business continuity. Many organizations adopt occupant emergency plans, OEPs, to guide and assist with sustaining personnel safety in the wake of a disaster. The OEP provides guidance on how to minimize threats to life, prevent injury, manage duress, handle travel, provide for safety monitoring, and protect property from damage due to a destructive physical event. The OEP does not address IT issues or business continuity, just personnel and general property. The Business Continuity Plan, BCP, and Disaster Recovery Plan, DRP, address IT and business continuity and recovery issues. Regulatory requirements. Every organization operates within a certain industry and jurisdiction. Both of these entities, and possibly additional ones, impose legal requirements, restrictions, and regulations on the practices of organizations that fall within their realm. These legal requirements can apply to licensed use of software, hiring restrictions, handling of sensitive materials, and compliance with safety regulations. Complying with all applicable legal requirements is a key part of sustaining security. The legal requirements for an industry and a country, and often also a state and city, must be considered a baseline or foundation on which the remainder of the security infrastructure is built. Key performance indicators of physical security. Key performance indicators, KPIs, of physical security should be determined, monitored, recorded, and evaluated. KPIs are metrics or measurements of the operation of or the failure of various aspects of physical security. The goal of the use of KPIs is to assess the effectiveness of security efforts. Only with such information can management make informed decisions on altering existing security operations in order to achieve a higher level of effective security protection. Keep in mind, the overall goal of security is to reduce risk so that the organization's objectives can be achieved in a cost-effective manner. Here are common and potential examples of physical security KPIs. Number of successful intrusions, number of successful crimes, number of successful incidents, number of successful disruptions, number of unsuccessful intrusions, number of unsuccessful crimes, number of unsuccessful incidents, number of unsuccessful disruptions, time to detect incidents, time to assess incidents, time to respond to incidents, time to recover from incidents, time to restore normal conditions after incident, level of organizational impact of incidents, number of false positives, that is, false detection alerts/alarms. A baseline should be established for each KPI and a record maintained of each measurement. This historical record and baseline are necessary to perform trend analysis and gain an understanding of the performance of the physical security mechanisms. Automatically collected KPIs are often preferred since they will be recorded reliably. However, manual KPI measurements are often more important, but they require attention and focus to collect. Each incident response operation, even if a BCP and DRP level issue, should conclude with a lessons learned phase where/when any additional KPI-related information is gathered or determined and recorded. With reliable KPI assessment, organizations can identify deficiencies, assess improvements, evaluate response measures, and perform return on security investment, ROSI, and cost/benefit analysis for physical security controls. Summary. In all circumstances and under all conditions, the most important goal of security is protecting people. Several elements are involved in implementing and maintaining physical security. One core element is selecting or designing the facility to house your IT infrastructure and the operations of your organization. You must start with a plan that outlines the security needs for your organization and develops through a process known as critical path analysis. Additional elements of a secure facility plan are to evaluate site selection and visibility requirements and consider facility design elements such as crime prevention through environmental design, CPTED. The security controls implemented to manage physical security can be divided into three groups: administrative, management, managerial or procedural, technical, logical, and physical. Administrative physical security controls include facility construction and selection, site management, building design, personnel controls, awareness training, and emergency response and procedures. Technical physical security controls include building access controls, intrusion detection, alarms, security cameras, monitoring, heating, ventilation and air conditioning, HVAC power supplies, and fire detection and suppression. Physical controls for physical security include fencing, lighting, locks, construction materials, access control vestibules, formerly known as man-traps, guard dogs, and security guards. Wiring closets and server rooms are important infrastructure elements that require protection. They often house core networking devices and other sensitive equipment. Protections include adequate locks, smart cards for authentication, proximity devices and readers, intrusion detection systems, cameras, surveillance, access control, and regular physical inspections. An important aspect of physical access control and maintaining the security of a facility is protecting the basic elements of the environment. This may include the use of media storage facilities, evidence storage, and work area restrictions. Providing clean power sources, minimizing interference, and managing the environment are also important. Fire detection and suppression must not be overlooked. In addition to protecting people, fire detection and suppression are designed to keep damage caused by fire, smoke, heat, and suppression materials to a minimum, especially in regard to the IT infrastructure. Additional physical security mechanisms to implement and manage include perimeter breach detection, fences, gates, turnstiles, access control vestibules, lighting, security guards, guard dogs, locks, badges, protected cable distribution, motion detectors, intrusion alarms, and secondary verification mechanisms. It is also essential to evaluate regulatory compliance and track KPIs. Exam Essentials. Understand why there is no security without physical security. Without control over the physical environment, No amount of administrative or technical/logical access controls can provide adequate security. If a malicious person can gain physical access to your facility or equipment, they can do just about anything they want, from destruction to disclosure and alteration. Understand a security facility plan. A secure facility plan outlines the security needs of your organization and emphasizes methods or mechanisms to provide security. Such a plan is developed through risk assessment and critical path analysis. Define critical path analysis. Critical path analysis is a systematic effort to identify relationships between mission-critical applications, processes, and operations, and all the necessary supporting elements. Know about technology convergence. Technology convergence is the tendency for various technologies, solutions, utilities, and systems to evolve and merge over time. Though in some instances this can result in improved efficiency and cost savings, it can also represent a single point of failure and become a more valuable target for malicious hackers and intruders. Understand site selection. Site selection should be based on the security needs of the organization. Cost, location, and size are important, but addressing the requirements of security should always take precedence. The key elements in making a site selection are visibility, composition of the surrounding area, and area accessibility. Know the key elements in designing a facility for construction. A key element in designing a facility for construction is understanding the level of security needed by your organization and planning for it before construction begins. Define CPTED. Crime prevention through environmental design, CPTED, is based on the idea to structure the physical environment and surroundings to influence individual decisions that potential offenders make before committing any criminal acts. Be able to list administrative physical security controls. Examples of administrative physical security controls are facility construction and selection, site management, building design, personnel controls, awareness training, and emergency response and procedures. Be able to list technical physical security controls. Technical physical security controls can be building access controls, intrusion detection, alarms, security cameras, monitoring, heating, ventilation and air conditioning, HVAC power supplies, and fire detection and suppression. Be able to name physical controls for physical security. Physical controls for physical security are fencing, lighting, locks, construction materials, access control vestibules, formerly known as man-traps, guard dogs, and security guards. Note the functional order of controls. These are deter, deny, detect, delay, determine, and decide. Understand equipment failure. No matter the quality of the equipment your organization chooses to purchase and install, eventually it will fail. Preparing for equipment failure may include purchasing replacement parts, storing equipment, or having an SLA with a vendor. Define MTTF, MTTR, and MTBF. Mean time to failure, MTTF, is the expected typical functional lifetime of the device given a specific operating environment. Mean time to repair, MTTR, is the average length of time required to perform a repair on the device. Mean time between failures, MTBF, is an estimation of the time between the first and any subsequent failures. Know how to design and configure secure work areas. There should not be equal access to all locations within a facility. Areas that contain assets of higher value or importance should have restricted access. Valuable and confidential assets should be located in the heart or center of protection provided by a facility. Understand the security concerns of a wiring closet. A wiring closet is where the networking cables for a whole building or just a floor are connected to other essential equipment, such as patch panels, switches, routers, LAN extenders, and backbone channels. Most of the security for a wiring closet focuses on preventing physical unauthorized access. If an unauthorized intruder gains access to the area, they may be able to steal equipment, pull or cut cables, or even plant a listening device. Understand smart cards. Smart cards are credit card-sized IDs, badges, or security passes with an embedded magnetic stripe, barcode, or integrated circuit chip. They contain information about the authorized bearer that can be used for identification and/or authentication purposes. Know about proximity devices and readers. A proximity device can be a passive device, a field-powered device, or a transponder. When it passes near a proximity reader, the reader device is able to determine who the bearer is and whether they have authorized access. Understand intrusion detection systems. Intrusion detection systems, IDSs, or burglar alarms are systems, automated or manual, designed to detect an attempted intrusion, breach, or attack, the use of an unauthorized entry point, or the occurrence of some specific event at an unauthorized or abnormal time. Know about cameras. Video surveillance, video monitoring, closed-circuit television, CCTV, and security cameras are all means to deter unwanted activity and create a digital record of the occurrence of events. Cameras can be overt or hidden, can record locally or to a cloud storage service, may offer pan, tilt, and zoom, may operate in visible or infrared light, may be triggered by movement, may support time-lapse recording, tracking, facial recognition, object detection, or infrared or color-filtered recording, and may offer face recognition, gait analysis, and/or object detection. Understand security needs for media storage. Media storage facilities should be designed to securely store blank media, reusable media, and installation media. The concerns include theft, corruption, and data remnant recovery. Media storage facility protections include using locked cabinets or safes, using a media librarian/custodian, implementing a check-in/checkout process, and using media sanitization. Understand the concerns of evidence storage. Evidence storage is used to retain logs, drive images, virtual machine snapshots, and other data sets for recovery, internal investigations, and forensic investigations. Protections include dedicated/isolated storage facilities, offline storage, activity tracking, hash management, access restrictions, and encryption. Know the common threats to physical access controls. No matter what form of physical access control is used, a security guard or other monitoring system must be deployed to prevent abuse, impersonation, masquerading, tailgating, and piggybacking. Know the terms commonly associated with power issues. Know the definitions of the following: fault, blackout, sag, brownout, spike, surge, inrush, ground, and noise. Understand how to control your environment. In addition to power considerations, Maintaining the environment involves control over the HVAC mechanisms. Rooms containing primarily computers should be kept at 59 to 89.6 degrees Fahrenheit, 15 to 32 degrees Celsius. Humidity in a computer room should be maintained between 20 and 80%. Too much humidity can cause corrosion. Too little humidity causes static electricity. Know about static electricity. Even on non-static carpeting, if the environment has low humidity, it is still possible to generate 20,000-volt static discharges. Even minimal levels of static discharge can destroy electronic equipment. Understand the need to manage water leakage and flooding. Water leakage and flooding should be addressed in your environmental safety policy and procedures. Plumbing leaks are not an everyday occurrence, but when they occur, they often cause significant damage. Water and electricity don't mix. If your computer systems come in contact with water, especially while they are operating, damage is sure to occur. Whenever possible, locate server rooms and critical computer equipment away from any water source or transport pipes. Understand the importance of fire detection and suppression. Fire detection and suppression must not be overlooked. Protecting personnel from harm should always be the most important goal of any security or protection system. In addition to protecting people, fire detection and suppression are designed to keep damage caused by fire, smoke, heat, and suppression materials to a minimum, especially in regard to the IT infrastructure. Understand the possible contamination and damage caused by a fire and suppression. The destructive elements of a fire include smoke and heat, but also the suppression medium such as water or soda acid. Smoke is damaging to most storage devices. Heat can damage any electronic or computer component. Suppression mediums can cause short circuits, initiate corrosion, or otherwise render equipment useless. All of these issues must be addressed when designing a fire response system. Know about physical perimeter security controls. Control access to a facility can be accomplished using fences, gates, turnstiles, access control vestibules, bollards, and barricades. Understand lighting. Lighting is the most commonly used form of perimeter security control, providing the security benefit of deterrence. Know about security guards and guard dogs. Guards can be posted around a perimeter or inside to monitor access points or watch detection and surveillance monitors. The real benefit of guards is that they are able to adapt and react to various conditions or situations. Guards can learn and recognize attack and intrusion activities and patterns, can adjust to a changing environment, and can make decisions and judgment calls. Guard dogs can be an alternative to security guards. They can often be deployed as a perimeter security control. As a detection and deterrent, dogs are extremely effective. Understand how to handle visitors in a secure facility. If a facility employs restricted areas to control physical security, then a mechanism to handle visitors is required. Often, an escort is assigned to visitors, and their access and activities are monitored closely. Failing to track the actions of outsiders when they are granted access to a protected area can result in malicious activity against the most protected assets. Understand internal security controls. There are many physical security mechanisms for internal control, including locks, badges, protective distribution systems, PDSs, motion detectors, intrusion alarms, and secondary verification mechanisms. Understand personnel privacy and safety. In all circumstances and under all conditions, the most important aspect of security is protecting people. Thus, preventing harm to people is the most important goal for all security solutions. Know about KPIs of physical security. Key performance indicators, KPIs of physical security, should be determined, monitored, recorded, and evaluated. KPIs are metrics or measurements of the operation of or the failure of various aspects of physical security. Written lab. 1. What kind of device helps to define an organization's perimeter and also serves to deter casual trespassing? Answer. A fence is an excellent perimeter safeguard that can help to deter casual trespassing. Moderately secure installations work when the fence is 6 to 8 feet tall and will typically be cyclone, also known as chain link fencing, with the upper surface twisted or barbed to deter casual climbers. More secure installations usually opt for fence heights over 8 feet and often include multiple strands of barbed or razor wire strung above the chain link fabric to further deter climbers. 2. What is the problem with halon-based fire suppression technology? Answer. Halon is an effective fire suppression compound. It starves a fire of oxygen by disrupting the chemical reaction of combustion. But it degrades into toxic gases at 900 degrees Fahrenheit. Also, it is not environmentally friendly. It is an ozone-depleting substance. The 1989 Montreal Protocol initiated the termination of manufacturing of ozone-depleting substances, which includes halon. In 1994, the EPA banned the manufacture of halon in the United States, as well as importing halon into the country. However, according to the Montreal Protocol, you can obtain halon by contacting a halon recycling facility. The EPA seeks to exhaust existing stocks of halon to take this substance out of circulation. Although, even in 2020, there are still significant domestic stockpiles of halon. 3. What kinds of potential issues can an emergency visit from the fire department leave in its wake? Answer. Anytime water is used to respond to fire, flame, or smoke, water damage becomes a serious concern, particularly when water is released in areas where electrical equipment is in use. Not only can computers and other electrical gear be damaged or destroyed by water, but also many forms of storage media can become damaged or unusable. Also, when seeking hot spots to put out, firefighters often use axes to break down doors or cut through walls to reach them as quickly as possible. This, too, poses the potential for physical damage to or destruction of devices and/or wiring that may also be in the vicinity. 4. What is CPTED? Answer. Crime Prevention Through Environmental Design, CPTED, is a well-established school of thought on secure architecture. The idea is to structure the physical environment and surroundings to influence individual decisions that potential offenders make before committing any criminal acts. CPTED addresses facility design, landscaping, entrance concepts, campus layouts, light, road placement, and traffic management of vehicles and those on foot. The core principle of CPTED is that the design of the physical environment can be managed, manipulated, and crafted with intention in order to create behavioral effects or changes in people present in those areas that result in reduction of crime as well as a reduction of the fear of crime. CPTED has 3 main strategies: natural access control, natural surveillance, and natural territorial reinforcement. 5. What are the 3 main types of proximity devices and how do they work? Answer. A proximity device can be a passive device, a field-powered device, or a transponder. The proximity device is worn or held by the authorized bearer. When it passes near a proximity reader, the reader device is able to determine who the bearer is and whether they have authorized access. The passive proximity device has no active electronics. It is just a small magnet with specific properties, like anti-theft devices commonly found in or on retail product packaging. A passive device reflects or otherwise alters the electromagnetic EM field generated by the reader device. This alteration is detected by the reader device, which triggers the alarm, records a log event, or sends a notification. A field-powered proximity device has electronics that activate when the device enters the EM field that the reader generates. Such devices actually generate electricity from an EM field to power themselves, such as card readers that require only that the access card be waved within inches of the reader to unlock doors. This is effectively the concept of radio frequency identification, RFID. A transponder proximity device is self-powered and transmits a signal received by the reader. This can occur consistently or only at the press of a button, like a garage door opener or car alarm key fob. Such devices may have batteries, capacitors, or even be solar-powered. Review questions. 1. Your organization is planning on building a new facility to house a majority of on-site workers. The current facility has had numerous security issues, such as loitering, theft, graffiti, and even a few physical altercations between employees and non-employees. The CEO has asked you to assist in developing the facility plan to reduce these security concerns. While researching options, you discover the concepts of CPTED. Which of the following is not one of its core strategies? A. Natural territorial reinforcement. B. Natural access control. C. Natural training and enrichment. D. Natural surveillance. Answer: C. Natural training and enrichment is not a core strategy of CPTED. Crime prevention through environmental design, CPTED, has three main strategies: natural access control, natural surveillance, and natural territorial reinforcement. Natural access control is the subtle guidance of those entering and leaving a building through placement of entranceways, use of fences and bollards, and placement of lights. Natural surveillance is any means to make criminals feel uneasy through the increasing of opportunities for them to be observed. Natural territorial reinforcement is the attempt to make the area feel like an inclusive, caring community. 2. What method is a systematic effort to identify relationships between mission-critical applications, processes, and operations, and all the necessary supporting elements when evaluating the security of a facility or designing a new facility? A. Log file audit. B. Critical path analysis. C. Risk analysis. D. Taking inventory. Answer: B. Critical path analysis is a systematic effort to identify relationships between mission-critical applications, processes, and operations, and all the necessary supporting elements when evaluating the security of a facility or designing a new facility. Log file audit can help detect violations to hold users accountable, but it is not a security facility design element. Risk analysis is often involved in facility design, but it is the evaluation of threats against assets in regard to rate of occurrence and levels of consequence. Taking inventory is an important part of facility and equipment management, but it is not an element in overall facility design. 3. Which of the following is a true statement in regard to security cameras? Choose all that apply. A. Cameras should be positioned to watch exit and entry points, allowing any change in authorization or access level. B. Cameras are not needed around valuable assets and resources, as well as to provide additional protection in public areas, such as parking structures and walkways. C. Cameras should be positioned to have clear sight lines of all exterior walls, entrance and exit points, and interior hallways. D. Security cameras should only be overt and obvious in order to provide a deterrent benefit. E. Security cameras have a fixed area of view for recording. F. Some camera systems include a system on a chip, SoC, or embedded components, and may be able to perform various specialty functions, such as time-lapse recording, tracking, facial recognition, object detection, or infrared or color-filtered recording. G. Motion detection or sensing cameras can always distinguish between humans and animals. Answer: A, C, and F. The true statements are option A. Cameras should be positioned to watch exit and entry points, allowing any change in authorization or access level. Option C. Cameras should be positioned to have clear sight lines of all exterior walls, entrance and exit points, and interior hallways. And option F. Some camera systems include a system on a chip, SoC, or embedded components, and may be able to perform various specialty functions such as time-lapse recording, tracking, facial recognition, object detection, or infrared or color-filtered recording. The remaining answer options are incorrect. The corrected statements for those options are: Option B. Cameras should also be used to monitor activities around valuable assets and resources, as well as to provide additional protection in public areas such as parking structures and walkways. Option D. Security cameras can be overt and obvious in order to provide a deterrent benefit, or hidden and concealed in order to primarily provide a detective benefit. Option E. Some cameras are fixed, whereas others support remote control of automated pan, tilt, and zoom, PTZ. And option G. Simple motion recognition or motion-triggered cameras may be fooled by animals, birds, insects, weather, or foliage. 4. Your organization is planning on building a new primary headquarters in a new town. You have been asked to contribute to the design process, so you have been given copies of the proposed blueprints to review. Which of the following is not a security-focused design element of a facility or site? A. Separation of work and visitor areas. B. Restricted access to areas with higher value or importance. C. Confidential assets located in the heart or center of a facility. D. Equal access to all locations within a facility. Answer: D. Equal access to all locations within a facility is not a security-focused design element. Each area containing assets or resources of different importance, value, and confidentiality should have a corresponding level of security restriction placed on it. A secure facility should have a separation between work and visitor areas and should restrict access to areas with higher value or importance, and confidential assets should be located in the heart or center of a facility. 5. A recent security audit of your organization's facilities has revealed a few items that need to be addressed. A few of them are related to your main data center, but you think at least one of the findings is a false positive. Which of the following does not need to be true in order to maintain the most efficient and secure server room? A. It must be optimized for workers. B. It must include the use of non-water fire suppressants. C. The humidity must be kept between 20 and 80%. D. The temperature must be kept between 59 and 89.6 degrees Fahrenheit. Answer: A. A computer room does not need to be optimized for human workers to be efficient and secure. A server room would be more secure with a non-water fire suppressant system. It would protect against damage caused by water suppressant. A server room should have humidity maintained between 20 and 80% relative humidity and maintain a temperature between 59 and 89.6 degrees Fahrenheit. 6. A recent security policy update has restricted the use of portable storage devices when they are brought in from outside. As a compensation, a media storage management process has been implemented. Which of the following is not a typical security measure implemented in relation to a media storage facility containing reusable, removable media? A. Employing a media librarian or custodian. B. Using a check-in/checkout process. C. Hashing. D. Using sanitization tools on returned media. Answer: C. Hashing is not a typical security measure implemented in relation to a media storage facility containing reusable, removable media. Hashing is used when it is necessary to verify the integrity of a data set, whereas data on reusable, removable media should be removed and not retained. Usually, the security features for a media storage facility include using a media librarian or custodian, using a check-in/checkout process, and using sanitization tools on returned media. 7. The company server room has been updated with raised floors and MFA door locks. You want to ensure that updated facility is able to maintain optimal operational efficiency. What is the ideal humidity range for a server room? A. 20 to 40%. B. 20 to 80%. C. 80 to 89.6%. D. 70 to 95%. Answer: B. The humidity in a computer room should ideally be from 20 to 80%. Humidity above 80% can result in condensation, which causes corrosion. Humidity below 20% can result in increased static electricity buildup. However, this does require managing temperature properly as well. The other number ranges are not the relative humidity ranges recommended for a data center. 8. You are mapping out the critical paths of network cables throughout the building. Which of the following items do you need to make sure to include and label on your master cabling map as part of crafting the cable plant management policy? Choose all that apply. A. Access control vestibule. B. Entrance facility. C. Equipment room. D. Fire escapes. E. Backbone distribution system. F. Telecommunications room. G. UPSs. H. Horizontal distribution system. I. Loading dock. Answer: B, C, E, F, and H. The primary elements of a cable plant management policy should include a mapping of the entrance facility, that is, demarcation point, equipment room, backbone distribution system, telecommunications room, and horizontal distribution system. The other items are not elements of a cable plant. Thus, access control vestibule, fire escapes, UPSs, and the loading dock are not needed elements on a cable map. 9. What is the best type of water-based fire suppression system for a computer facility? A. Wet pipe system. B. Dry pipe system. C. Pre-action system. D. Deluge system. Answer: C. A pre-action system is the best type of water-based fire suppression system for a computer facility because it provides the opportunity to prevent the release of water in the event of a false alarm or false initial trigger. The other options of wet pipe, dry pipe, and deluge system use only a single trigger mechanism without the ability to prevent accidental water release. 10. Your company has a yearly fire detection and suppression system inspection performed by the local authorities. You start up a conversation with the lead inspector, and they ask you, what is the most common cause of a false positive for a water-based fire suppression system? So, what do you answer? A. Water shortage. B. People. C. Ionization detectors. D. Placement of detectors in drop ceilings. Answer B. The most common cause of a false positive for a water-based system is human error. If you turn off the water source after a fire and forget to turn it back on, you'll be in trouble for the future. Also, pulling an alarm when there is no fire will trigger damaging water release throughout the office. Water shortage would be a problem, but it is not a cause for a false positive event. Ionization detectors are highly reliable, so they are usually not the cause of a false positive event. Detectors can be placed in drop ceilings in order to monitor that airspace. This would only be a problem if another detector was not placed in the main area of the room. If there are only detectors in the drop ceiling, then that could result in a false negative event. 11. A data center has had repeated hardware failures. An auditor notices that systems are stacked together in dense groupings with no clear organization. What should be implemented to address this issue? A. Visitor logs. B. Industrial camouflage. C. Gas-based fire suppression. D. Hot aisles and cold aisles. Answer. D. The cause of the hardware failures is implied by the lack of organization of the equipment, which is heat buildup. This could be addressed by better management of temperature and airflow, which would involve implementing hot aisles and cold aisles in the data center. A data center should have few, if any, actual visitors, such as outsiders. But anyone entering and leaving a data center should be tracked and recorded in a log. However, whether or not a visitor log is present has little to do with system failure due to poor heat management. Industrial camouflage is not relevant here, since it is about hiding the purpose of a facility from outside observers. A gas-based fire suppression system is more appropriate for a data center than a water-based system, but neither would cause heat problems due to poor system organization. 12. Which of the following are benefits of a gas-based fire suppression system? Choose all that apply. A. Can be deployed throughout a company facility. B. Will cause the least damage to computer systems. C. Extinguishes the fire by removing oxygen. D. May be able to extinguish the fire faster than a water discharge system. Answer: B, C, and D. Benefits of gas-based fire suppression include causing the least damage to computer systems and extinguishing the fire quickly by removing oxygen. Also, gas-based fire suppression may be more effective and faster than a water-based system. A gas-based fire suppression system can only be used where human presence is at a minimum, since it removes oxygen from the air. 13. When designing physical security for an environment, it is important to focus on the functional order in which controls should be used. Which of the following is the correct order of the 6 common physical security control mechanisms? A. Decide, delay, deny, detect, deter, determine. B. Deter, deny, detect, delay, determine, decide. C. Deny, deter, delay, detect, decide, determine. D. Decide, detect, deny, determine, deter, delay. Answer: B. The correct order of the 6 common physical security control mechanisms is deter, deny, detect, delay, determine, decide. The other options are incorrect. 14. Equipment failure is a common cause of a loss of availability. When deciding on strategies to maintain availability, it is often important to understand the criticality of each asset and business process, as well as the organization's capacity to weather adverse conditions. Match the term to the definition. Roman numeral 1, MTTF. Roman numeral 2, MTTR. Roman numeral 3, MTBF. Roman numeral 4, SLA. 1. Clearly defines the response time a vendor will provide in the event of an equipment failure emergency. 2. An estimation of the time between the first and any subsequent failures. 3. The expected typical functional lifetime of the device given a specific operating environment. 4. The average length of time required to perform a repair on the device. A. Roman numeral 1, 1. Roman numeral 2, 2. Roman numeral 3, 4. Roman numeral 4, 3. B. Roman numeral 1, 4. Roman numeral 2, 3. Roman numeral 3, 1. Roman numeral 4, 2. C. Roman numeral 1, 3. Roman numeral 2, 4. Roman numeral 3, 2. Roman numeral 4, 1. D. Roman numeral 1, 2. Roman numeral 2, 1. Roman numeral 3, 3. Roman numeral 4, 4. Answer. C. Mean time to failure, MTTF, is the expected typical functional lifetime of the device given a specific operating environment. Mean time to repair, MTTR, is the average length of time required to perform a repair on the device. Mean time between failures, MTBF, is an estimation of the time between the first and any subsequent failures. A service level agreement, SLA, clearly defines the response time a vendor will provide in the event of an equipment failure emergency. 15. You have been placed on the Facility Security Planning Team. You've been tasked to create a priority list of issues to address during the initial design phase. What is the most important goal of all security solutions? A. Prevention of disclosure. B. Maintaining integrity. C. Human safety. D. Sustaining availability. Answer. C. Human safety is the most important goal of all security solutions. The top priority of security should always be the protection of the lives and safety of personnel. The protection of CIA, confidentiality, integrity, and availability of company data and other assets is the second priority after human life and safety. 16. While reviewing the facility design blueprints, you notice several indications of a physical security mechanism being deployed directly into the building's construction. Which of the following is a double set of doors that is often protected by a guard and is used to contain a subject until their identity and authentication are verified? A. Gate. B. Turnstile. C. Access control vestibule. D. Proximity detector. Answer. C. An access control vestibule is a double set of doors that is often protected by a guard and used to contain a subject until their identity and authentication is verified. A gate is a doorway used to traverse through a fence line. A turnstile is an ingress or egress point that allows travel only in one direction and by one person at a time. A proximity detector determines whether a proximity device is nearby and whether the bearer is authorized to access the area being protected. 17. Due to a recent building intrusion, facility security has become a top priority. You are on the proposal committee that will be making recommendations on how to improve the organization's physical security stance. What is the most common form of perimeter security devices or mechanisms? A. Security guards. B. Fences. C. CCTV. D. Lighting. Answer. D. Lighting is often claimed to be the most commonly deployed physical security mechanism. However, lighting is only a deterrent and not a strong deterrent. It should not be used as the primary or sole protection mechanism except in areas with a low threat level. Your entire site, inside and out, should be well lit. This provides for easy identification of personnel and makes it easier to notice intrusions. Security guards are not as common as lighting, but they are more flexible in terms of security benefits. Fences are not as common as lighting, but they serve as a preventive control. CCTV is not as common as lighting, but serves as a detection control. 18. Your organization has just landed a new contract for a major customer. This will involve increasing production operations at the primary facility, which will entail housing valuable digital and physical assets. You need to ensure that these new assets receive proper protections. Which of the following is not a disadvantage of using security guards? A. Security guards are usually unaware of the scope of the operations within a facility. B. Not all environments and facilities support security guards. C. Not all security guards are themselves reliable. D. Pre-screening, bonding, and training do not guarantee effective and reliable security guards. Answer A. Security guards are usually unaware of the scope of the operations within a facility and are therefore not thoroughly equipped to know how to respond to every situation. Though this is considered a disadvantage, the lack of knowledge of the scope of the operations within a facility can also be considered an advantage, because this supports confidentiality of those operations and thus helps reduce the possibility that a security guard will be involved in the disclosure of confidential information. Thus, even though this answer option is ambiguous, it is still better than the three other options. The other three options are disadvantages of security guards. Not all environments and facilities support security guards. This may be because of actual human incompatibility or the layout, design, location, and construction of the facility. Not all security guards are themselves reliable. Pre-screening, bonding, and training do not guarantee that you won't end up with an ineffective or unreliable security guard. 19. While designing the security plan for a proposed facility, you are informed that the budget was just reduced by 30%. However, they did not adjust or reduce the security requirements. What is the most common and inexpensive form of physical access control device for both interior and exterior use? A. Lighting. B. Security guard. C. Key locks. D. Fences. Answer C. Key locks are the most common and inexpensive form of physical access control device for both interior and exterior use. Lighting, security guards, and fences are all much more costly. Fences are also mostly used outdoors. 20. While implementing a motion detection system to monitor unauthorized access into a secured area of the building, you realize that the current infrared detectors are causing numerous false positives. You need to replace them with another option. What type of motion detector senses changes in the electrical or magnetic field surrounding a monitored object? A. Wave. B. Photoelectric. C. Heat. D. Capacitance. Answer D. A capacitance motion detector senses changes in the electrical or magnetic field surrounding a monitored object. A wave pattern motion detector transmits a consistent low ultrasonic or high microwave frequency signal into a monitored area and monitors for significant or meaningful changes or disturbances in the reflected pattern. A photoelectric motion detector senses changes in visible light levels for the monitored area. Photoelectric motion detectors are usually deployed in internal rooms that have no windows and are kept dark. An infrared PIR, passive infrared, or heat-based motion detector monitors for significant or meaningful changes in the heat levels and patterns in a monitored area.